Nuclear reactors work by smashing a heavy element like uranium or plutonium into pieces in a process called nuclear fission. A neutron is fired at a fissionable nucleus that will split into two products and a few neutrons, which will fission other nuclei. Energy in the form of heat is released from the shattered nucleus. The heat flashes water into steam to spin a series of turbines. The theory behind nuclear power plants and coal power plants are very similar. They both source energy from heat and use that to spin a turbine. Coal just sources its heat from breaking chemical bonds instead of fissioning nuclei. The bonds are broken in a combustion reaction, creating carbon dioxide, water, and heat as byproducts. The big difference is how much fuel is needed to produce an amount of energy.
You want to be aware of what the power density of any source is. Anybody who's trying to sell you biofuels or this kind of thing, what do you do about the thermodynamic inefficiency of combustion engines? Fuels that you burn is down in here. Whenever we burn something, we're using a very inefficient process. Thermodynamics typically gives us about 30% of the energy when we burn fuel.
Every kilogram of fissile material will produce as much energy as 13,000 barrels of oil. Nuclear fission is 1,000,000 times more energy dense than a chemical reaction.
If you move up to fission, you got hundreds of thousands more watts per square foot, per acre, per pound, whatever. And if you move up to fusion, you get another 10,000 times that.
It's an amazing difference in the amount of fuel needed to provide an amount of energy. Such a large amounts of oil or coal contain as much usable energy as such a small amount of thorium or uranium. This technology has a long history. Practical use began in World War II, where the Manhattan Project spurred the development of nuclear technologies to gain an upper hand in the war. Great amounts of research went into the development of uranium and plutonium weaponry. Their research, along with their contemporaries, is the foundation of nuclear energy technology. They used reactors, now referred to as Generation 1, to breed plutonium from uranium, a process used in some nuclear power plants today. Generation 2 reactors were most frequently used for power plants. Using methods learned and technology developed during World War II, these reactors fissioned solid fuels like uranium dioxide. The pressurized light water reactor is susceptible to losing coolant pressure, the cause of the 1979 Three Mile Island accident. Nobody was harmed, though. Generation 3 reactors are the safety-focused evolution of Generation 2 reactor design. The design improvements include foci like passive safety and longer lifespan, though very few are operational. The next generation of nuclear reactors, Generation 4, consists of experimental technologies designed to be safer and more economical. These include higher fuel efficiency and using fuels not fit for weapons. Generation 2 and 3 reactors aren't able to properly use the majority of their fuel.
The heavy water reactor will use about 0.7% of the uranium's energy value, and the light water reactor will use about half of 1%.
This inefficiency is due to the solid nature of their fuels, which capture fission products. Recycling is possible but uneconomical. Molten salt reactors use a liquid fuel where gaseous fission products can rise out and solid products can sink to the bottom of the fuel. The most promising fuel for these is thorium tetrafluoride. Thorium-232 is a common, slightly radioactive isotope with an extremely long half-life.
Thorium is a naturally occurring nuclear fuel that is 4 times more common in the Earth's crust than uranium.
When it captures a neutron, it beta decays into protactinium-233, which beta decays into uranium-233, a fissile isotope. The liquid fluoride thorium reactor, LIFTR, uses this beta decay chain to obtain fissile uranium-233 from the relatively common thorium, found in rare earth metal deposits. There are roadblocks to implementing this technology, however.
Currently, nuclear power is not allowed in the state of Kentucky.
Burning fossil fuels is what society has been doing for power for over 100 years. That's what it's accustomed to. Regulation reflects this.
We have a 3-year environmental assessment process in Canada to build a nuclear reactor, and we have a weekend to produce a coal plant.
Coal and gas plants are able to release radioactive materials to the environment in much greater amounts than a nuclear plant would ever possibly be allowed to, because they are considered what's called NORM, naturally occurring radioactive materials.
The problem with NORM is that the natural radioactive material is taken from one place to another, decreasing background radiation at its source, but significantly increasing radiation where it's stored and burned.
For instance, when you go frack a shale and you pull gas out, a lot of radon comes out with that too. You burn the gas, that radon's being released. Nobody counts that radon against the gas. If they did, The Regulatory Commission would shut the gas plant down.
Radon naturally and slowly seeps out of the ground as a decay product of uranium, and it makes up about half of the average person's radiation exposure per year. Though it's nothing to worry about unless heavily concentrated, as the lowest annual dose linked to an increased cancer risk is 50 times the dose that a year of atmospheric radon exposure provides.
Coal contains small amounts of uranium and thorium. They go up the stack, they're dispersed.
Why they can't tell you how much waste they produce.
Yeah.
We have been burning coal since before radiation was discovered. If coal were to be proposed as a power source today, it would be shot down for the radioactive fly ash it emits. But we still use it because
We have access to low-cost coal